screen. Okay, it's 2:59, so we will wait a little bit.
Assalamu alaikum, ma'am.
Walaikum salam. Okay, let's wait until 3. Okay, so it's 3 o'clock, so I think we can go ahead and start now. So last time we were talking about nuclear transformations. We had finished our previous chapter, which was nuclear structure. The nuclear structure was a relatively easier chapter. It was a short chapter as well. So we talked about radioactive decay last time, and we talked about this diagram and the different types of radioactive decay and their penetrative power of alpha, beta, and beta particles and gamma rays. And we talked about the different types of 5 kinds of radioactive decay and the reasons for the instability due to which we get the radioactive decay. Then we did an example here, what kind of decay would it undergo. Then we talked about activity and a half-life. Okay, and I'm not going to go through all of this again because we already did these things last time. We had equation for decay constant in terms of half-life. Then we talked about radioactive decay, and we had an equation for the number n of undecayed nuclei as a function of the time t, in terms and as a function of the time t, and in terms of the decay probability per unit time lambda. ठीक है, lambda is the decay constant, which is the probability per unit time of decay. ठीक है, तो हमारे पास हमने एक और एग्जांपल भी ये कर लिया था. फिर हमने कहा था कि mean lifetime is 1 over lambda, where lambda is the decay constant here. ठीक है, so mean lifetime is, we can write it in terms of half-life, and then we did up till here. ठीक है, we did R activity is equals to lambda n because we had this equation. ठीक है, we said that the activity of a radioactive sample is defined as minus dn by dt, and dn by dt, we already had an equation for that, so we just substituted that equation in here. And we know that this one, we had R is equals to R naught e power minus lambda t. So R naught, we make it equal to lambda n naught. So in general, R becomes equals to lambda n. So now let's do an example. This was where we stopped last time. So we'll do an example now. Okay? So find the activity of, and this we have like 50 slides over in this PowerPoint. Okay? So we have things to do still. So and then we have one more chapter after this as well. So find the activity of 1 milligram of radon, 222 radon, whose atomic mass is 222 U. So the decay constant of radon is given by 0.693 divided by half-life. We already know this equation, okay? So 0.693. If we know what the half-life is, which is 3.8 days, and I would obviously give that to you, okay? We have to find the activity of a 1 milligram of radon. So if we know what its half-life is, we can find the decay constant, which is this. And then the number of atoms, we know that our activity is lambda n. So lambda is this number over here, and capital N is given by, what is capital N? The number of atoms in 1 gram of 222 radon. So 1 milligram is 10 power minus 6 kilograms. So we're writing this in terms of kilograms. So we have number of atoms in 1 milligram of 222 radon is the mass divided by its, what would that be, divided by the mass of one atom. The total mass, the number of atoms would be the total mass divided by the mass of one of the atoms. ठीक है? So we divide this mass over here, that 1 milligram of radon, divided by, it has 222, its mass number is 222, so we divide that by 222 U, and each U is equals to 1 atomic mass unit, which is U is equals to 1.66 times 10 raised to power minus 27 kilograms. So when we multiply this 222U in terms with its conversion factor, we get the mass of the 222 radon of one atom of that. So total mass divided by the mass of one atom will give you 2.71 10 raised to power 18 atoms. So now we have N, we have lambda. Can we find the activity? Yes, we can. So we just multiply those two numbers together. We get this much. This is in terms of atoms or nuclei. So we get, and what did we say was we just multiply these two together, we get this number of nuclei will decay per second. This number of nuclei per second, which means this one number of decays per second. Okay? And in terms of becquerel and the Curie units, we already mentioned those units before. Okay? 1 becquerel is 1 decay per second, and 1 Curie is 3.7. 1 Curie is 37 gigabecquerel. So in terms of those units, where did that go? Here, in terms of those units, we have to write it in terms of those units. So obviously 1 becquerel, 1 decay per second is something like 1 gigabecquerel, right? I mentioned it over here. 1 gigabecquerel is equals to what do you call it? 1 decay per second is 1 becquerel. So that was in terms of terabecquerel. Okay? Is that making sense? Here, so this is in terms of tera is 10 power 12, so that's why we have a terabecquerel. And in terms, if you want to convert that into curies, you will just use a conversion factor where 1 curie is equals to, and I mean, I would probably give you the conversion factor, so you don't have to memorize that. 1 curie is 37 gigabecquerel, so you just have to do the conversion over there. Okay, so we did this example. Where are we? Okay, so we are here. We just did this example, and now we will do another example. Okay. So what will be the activity of the above radon sample in exactly 1 week later? So we have this equation. Okay. So the initial, where R activity is equals to the R naught, which is the activity at the beginning, which we just found in the previous slide, is equals to 155 curies. So if we want to write in terms of curies, the initial, the R naught is the activity at the beginning of this 1 week. So we put that value in here. And then we want to find lambda T. So we already found lambda in this previous example. We'll multiply by that one, by the number of seconds in 1 week, which is 7 days, multiplied by how many seconds are there in 1 day? 24 hours times 3600, right? Which is 86,400 seconds per day. 24 hours in 1 day multiplied by 3600 seconds per hour. So we get 86,400 seconds per day, okay? So we multiply that by 7 days, and then we multiply with that by lambda. We will get lambda T is equals to 1.28. So then we get R is equals to R naught e power minus lambda T, so we get 43 curies. Okay? Any questions so far? Okay, no questions as usual. So I guess we will talk about another topic here. This is radiometric dating. So now what we can say is that why is this useful for us? This half-life and decay constant and all these things that we are doing up till now. Why is that useful for us? Well, basically it's called geological dating, which means that you can, if you have a piece of an object, a nuclide radioactive material, and you can, if you know what its activity is at a certain time, if you know what its current activity is, you can determine, and know what its half-life is, you can basically determine how old that sample is. Okay? Radioactivity makes it possible to establish the ages of many geological biological specimens. Basically, if you have geological or biological specimens, you can determine what their age is if you know what its half-life is and the amount that is present, or because the decay of any particular is independent of its environment, because radioactive decay is basically one important property of radioactive decay is that it's independent of its environment. Okay, so the ratio between the amounts of the nuclide and its stable daughter in a specimen depends on the latter's age. So basically what we're saying here, we will use an example to basically we will do an example here that will help you understand what radioactive dating means. Okay? It means that you can use for example, a piece of wood from the ruins of an ancient dwelling was found to have an activity of 13 disintegrations per minute per gram of its carbon content. To get the 14C carbon activity of living wood is 16 disintegrations. If you know what the activity is of living wood and what has already been like, for example, the 14C activity of 13 disintegrations per minute of its carbon content, the ruins, you can determine how old those ruins were. Okay? So basically we're saying here, how long ago did the tree die from which the wood sample came? So we're saying that 14C carbon, this tree sample, this wood over here, this ruins of wood, this tree sample died a long time ago, and we want to figure out how long ago did that tree die. Okay? So we're saying that the 14C carbon, which is its carbon content, it is 16 disintegrations per minute per gram of living wood. Okay? But the one that has died is found to have an activity of 13 disintegrations per minute per gram of its carbon content. So now let's use this example to figure out how long that tree is, how old that tree, how long ago did that tree die. So if the activity of a certain mass of carbon from a plant or animal was recently alive, is R naught, and the activity of the same mass is, so we have this formula R is equals to R naught e power minus lambda t, okay? So we know what the half-life of carbon 14 is, which is 5,760 years, okay? So we can evaluate its decay constant, okay? And I would give you some of these important values that are necessary to solve the problem. Then over here, we know that R is equals to R naught e power minus lambda 2. We know we have the R and the R naught. We know what the values are. Okay? R naught is its initial disintegration, which is R naught is 16, and R here is 13. Okay? R naught is 16 of living wood, what it was previously. Okay? Living wood का disintegration 16 into disintegration 16 decays per minute per gram था, ठीक है? So its R naught is 16 and its R is 13, which is the current value of its activity. And then we rearrange this equation over here, make T the subject of the equation as we did before. So e power lambda t is equals to R naught over R. Lambda t is equals to ln R naught over R. So we get this equation now. Now in this equation, we will put in 1 over lambda, the value of 1 over lambda, which is 0.5760 years divided by 0.693 into ln 16 over 13. So we get this much in terms of years. So this is how long ago that tree died. So how long ago did the tree die from which the wood sample came? It's 1.7 and 10 raised to power 3 years. Tika, any questions related to this example? Now this is what we mean by being able to date these samples, the radioactive samples, that were being able to date them, like how long ago they are, like how old they are, or how long ago they died, or something like that. Okay?
मैम
So
ये एक्टिविटी और नंबर ऑफ न्यूक्लियाई प्रोपोर्शनल है ना एक दूसरे के, क्योंकि
yeah,
फॉर्मूला सेम है ना?
फॉर्मूला तो मैंने आपको ये बताया था ना, activity is lambda times n, where n is the number of nuclei that are remaining and r is the activity. They're related by this formula.
तो नंबर ऑफ न्यूक्लियाई का भी तो यही फॉर्मूला होता है, n is equal to n naught e exponent negative lambda t.
उसका भी यही होता है, और activity का भी इसी तरह से होता है. So that's why so it is proportional, right? As you can see, the lambda is a proportionality constant, right? R is proportional to n, with lambda is the decay constant is a proportionality constant here. ठीक है?
Okay, ma'am. Thank you.
You're welcome. So basically what we're saying here is that we have this equation now for the age of a particular nuclei, a sample, okay? And you can write it in terms of n naught over n, or we can even write it in terms of r. In terms of r, it would be given by this formula. In terms of n, it would be given by this formula, n and n naught. And this, in terms of R and R naught, it would be given by this formula. Okay? So basically what they're saying is that if you have a rock sample or any sample of wood or something like that, you can determine, if we know what it's the half-life of that particular carbon or whatever it's made out of, the radioactive substance, we're able to determine how old it was. Okay? So we have done that. Now we'll be doing a little bit more about alpha decay, and then I will give you a small assignment here to derive one equation, and then we will do some more examples, etc. So we do have a lot more still to do. So let's see now. Alpha decay, as we did before, we will go a little bit more detail now in this alpha decay. So what did we know about alpha decay is that when we know about alpha decay is that when a sample, when a substance, when it's decaying by alpha decay, it will form, we get what we have. We start off with the parent nuclei, and then it becomes the daughter nuclei with the release of an alpha particle. So Q, the energy Q released when various particles are emitted. So in terms of for alpha decay, the disintegration energy is the energy that is released when the alpha particle is released from the nucleus. So this is called the disintegration energy. So it's given by Q is equals to M. This is Mi minus Mf minus Mx bracket में per multiplied by c squared. So we already know that E is equals to mc square, right? ये तो हमें पता है कि वो उसके energy equivalent of the mass is Me is equals to mc square. So here we're saying that Mi is the mass of the parent or the initial nucleus, ठीक है? Mf is the mass of the final nucleus. You will have to minus the mass of the final nucleus minus the mass of the alpha particle. Okay? And then you will multiply all of that by c squared, because this is the mass difference between the left-hand side of the equation and the right-hand side of the equation. Then you will multiply by c squared, you will get the disintegration energy, which is the energy equivalent, which is the energy released when the alpha particles are emitted from a heavy nucleus. Okay? So the emission of alpha particle in some cases is energy. Okay, so basically the kinetic energy, now we're interested in the kinetic energy of the emitted alpha particle. Now we're saying that the kinetic energy of this emitted alpha particle is never quite equal to the disintegration energy, because since momentum must be conserved, the nucleus recoils with a small amount of kinetic energy when the alpha particle emerges. Now, as a small assignment, I'm going to tell you to derive this equation, which is the alpha particle kinetic energy. It's approximately equal to A minus 4 divided by A into Q. Q here is this thing, the disintegration energy, okay? And this is the kinetic energy with which the alpha particle emerges. It's not exactly equal to the disintegration energy, but it's A minus 4 divided by A times Q. And where did this equation come from? That will be your next assignment, okay? And that can be due by next Monday, 1 week from now, okay? So I hope that you'll be able to do this assignment. It's not very difficult. It's not very long either, but you can just try to see how to do this, okay? So the nucleus recoils with a small amount of kinetic energy when the alpha particle emerges. It's easy to show from momentum. You have to use momentum and energy conservation here. That kinetic energy alpha is related to Q and mass number of the original nucleus. A here is the mass number of the original nucleus, okay? So you will use momentum and energy conservation to derive this formula. So this will be assignment number 4 in this class. Okay? And be due by next Monday. So the mass numbers of nearly all alpha emitters exceed 2 under 10. So most of the disintegration energy appears as the kinetic energy of the alpha particle. As you can see that the mass numbers of nearly all those nuclei that emit, nearly all those atoms that nuclei that emit alpha particles exceed 210. That means A will be almost more than greater than 210 in most cases. So most of the disintegration energy appears as a kinetic energy, because 210 minus 4 divided by 210 is quite small. Actually it is close to 1. It's close to 1. Okay? So therefore it will be almost equal to Q, but this is the formula that you will derive. So now let's do another example. Let's do another example here, that the polonium isotope 21084P polonium is unstable, emits 5.3 mega electron volts alpha particle. the atomic mass of polonium is this, and of the alpha particle is this. Okay, now they've given you the kinetic energy of the alpha particle. They're saying identify the daughter nuclide, find its atomic mass. Now they've given us the kinetic energy, okay? So what do we have to do? Identify the daughter nuclide. What particle is the daughter nucleus? So let's see. So obviously, if this has a proton number of 84, 84 minus 2 हो जाएगा. Proton number 2 से कम हो जाएगा. Mass number 4 से कम हो जाएगा. So we have a particle that has mass number now. Now the daughter nucleus has mass number 206 and atomic number 82. So it is this is a lead. ठीक है? It's the atomic number of lead. So we get the lead. So the daughter nucleus in nuclide is for lead. 206, 82 lead. Pb is the symbol for lead. Okay? So find the atomic mass. So now we have the kinetic energy they've given us is 5.3 mega electron volts. So we have the kinetic energy. We rearrange this formula over here to make Q. We want to find the disintegration energy. Okay? We want to find Q. They're saying find its atomic mass. Q जब find करेंगे, the pair mass of the which particle are we trying to find the mass of? We're trying to find the mass equivalent with the atomic mass. We're trying to find the atomic mass of the daughter nuclide, ठीक है? तो ये हम इस formula, the daughter nuclide here is MF, the mass of the final nucleus. So MF is what we want to find. So when we rearrange this formula over here to make Q the subject, we will get this formula. Then put in A, because A is 210 because that is of the initial nucleus, original nucleus, and 210 minus 4 times 5.3 mega electron volts, you get 5.4 mega electron volts. ठीक है? So the mass equivalent of this Q value is MQ. ठीक है? MQ, what is MQ over here? This is the mass equivalent, ठीक है? Is equals to this Q in mega electron volts. We want to find out what is this mass in terms of energy. So you will just put in 5.4 mega electron volts divided by the number of mega electron volts per atomic mass unit to figure out what is the mass equivalent of this Q. ठीक है? So we found it to be this 0.0058 U. ठीक है? And then this. So the mass equivalent of this is MQ is equals to MI minus MF minus MX. So basically here, X is the alpha particle. So we know what MQ is the mass equivalent, the mass difference between the mass difference, which is equivalent to this energy difference. Okay? So then we will set, we know that, wait a minute. We know that this MQ is equals to MF is the mass difference, right? So it's MF minus this will be MI minus MF, ठीक है, minus M alpha. ठीक है? So when you rearrange this equation, this is I, this is MI. When you rearrange this equation, you will get, this is what we want to find. So and take that over there and take this over here. Okay? So we get this equation. So when you just plug in all the values, MI is for MI is the mass equivalent of MI is this. Where how did we get this number? This is the mass equivalent for that is for 210. Okay? And this is the mass of the equivalent of the alpha particle, polonium. Okay? Mass equivalent of the polonium, mass equivalent of this, and this is the mass difference, so we get this thing. So now how do we get MI as this thing, this value? From 210. Oops. I think this is given to us in the sum. This is given to us, okay? I would give you the value of what the mass equivalent is of that, okay? Yeah, so is there any question up till here? No question? Okay, then we will continue here with beta decay. So like alpha decay, beta decay, so we've done alpha decay, we've done an example related to that. We did radiometric radiocarbon dating, geological dating, and we did examples related to the half-life and the other things. So now let's do beta decay, okay? Where are we? Here. So beta decay, like alpha decay, beta decay is a means whereby a nucleus can alter its composition to become more stable. Okay, so what we talked about previously in the previous PowerPoint, we talked about beta decay as a neutron. We talked about beta decay as a neutron that breaks down into a proton and an electron. And we talked about positron emission, where a proton breaks down to a neutron and with the release of an electron. And we talked about electron capture, where we have a proton and an electron. They combine to form a neutron. However, there's some problems with these previous beta decay formulas that I mentioned, and we have to actually make sure that we have conservation of energy, linear momentum and angular momentum must be there. So the problems with the previous equations for beta decay that I mentioned is that they do not conserve linear momentum, energy, and angular momentum. So we have to introduce neutrinos, actually, and antineutrinos into this whole system, into these equations for beta decay. So before we go into what neutrinos are, we've already discussed a little bit about neutrinos previous course, a little bit before, but I will mention it here that the electron energy is observed. There's some properties, so some important things that we have to, some 1, 2, 3 points that we have to note down over here. Electron energies observed in beta decay are found to vary continuously from 0 to a maximum value Ke. ठीक है, so the electron energies जो हमारे पास बीटा डिके होता है, ठीक है, बीटा डिके का कौन सा फॉर्मूला था, ये फॉर्मूलाज होते हैं, ये फॉर्मूला, ठीक है. So electron energy over here can vary continuously from 0 to a maximum value of kinetic energy, ठीक है. I did not put a figure over here. I don't think that was so important, but basically in the energy spectrum there's a peak somewhere. I think I didn't put that formula here. There was a figure here somewhere. Let me show you that figure. 12.8. 12.10. Okay, just 1 second. Here we go. Energy spectrum of electrons from beta decay of 210 beryllium. Okay. So we have this energy. This is the energy diagram for the energy equivalent energy spectrum of the electrons. So as you can see, there's a peak over here, and this is we reach the maximum energy over here. Okay. Relative number of electrons that reaches a peak over here, and here we get the maximum energy. So why is this important to us? The maximum energy is given by E max is equals to mc squared plus kinetic energy max, because energy includes rest energy, okay, plus kinetic energy. So 1.17, this 1.17 is the maximum kinetic energy, electron energy that you can achieve, okay. Maximum energy, kinetic energy of the electron is 1.17 mega electron volts for the beta decay of 21083 Bi, okay, which is beryllium, I think so. So we have E max is equals to mc squared plus kinetic energy. Bismuth? Okay, sorry about that. Okay, so we have E max equals to mc squared plus kinetic energy maximum. So this formula is important because mc squared is the rest energy and K is the maximum kinetic energy, ठीक है? तो जितनी ज़्यादा energy होगी reaction की, this will be the rest energy, and the rest will go into the kinetic energy of the electron. So this, the maximum energy carried off by the decay electron is equal to the energy equivalent of the mass difference between the parent and daughter nuclei. Yeah. So basically जो parent nucleus है और जो daughter nucleus है, उनके दरमियान उनका जो mass difference होगा, ठीक है? That is carried off as energy. The energy equivalent of that mass difference is carried off by the decay electron, ठीक है? In the beta decay. Yeah. So But however, seldom, however, is the emitted electron found with an energy of K electron kinetic energy maximum, because obviously there's some losses of energy, okay? So when the direction of the emitted electron and of the recoiling nuclei are observed, they're almost never exactly opposite as required for linear momentum to be conserved. So basically what they're saying over here is that जो हमने previous beta decay के ये equations कहा था, beta decay में ये neutron will decay into proton plus electron. There are problems with these equations over here. There are problems with this equation beta decay here, because conservation of momentum and conservation of angular momentum, linear momentum, energy में कोई मसला आ रहा है. So we have to introduce neutrinos basically. The spin of neutron, proton, electrons are all 1/2. If beta decay involves just a neutron becoming a proton electron, spin is not conserved. Spin and angular momentum are related quantities, ठीक? So if spin must be conserved, which means that angular momentum must also be, if spin is conserved, then angular momentum will also be conserved. If spin is not conserved, angular momentum will also not be conserved. So we have to make sure that spin is conserved so that angular momentum will also be conserved, okay? And the only way that this equation the beta decay equation will make sense by conservation laws to hold true, okay? Like we want total energy to be conserved, we want spin to be conserved, angular momentum, linear momentum, all these things to be conserved will only be possible if we introduce neutrinos and antineutrinos into this equation. So the previous equations that we discussed had some problems with them. And so later Pauli, in 1930, Pauli proposed a desperate remedy for this solution to that conservation laws issue. So if an uncharged particle is of small or zero rest mass and spin 1/2 is emitted in beta decay, together with the electron, the above discrepancies would not occur. So basically what Pauli said later, he came up with a remedy where he introduced the neutrino and the antineutrino. So neutrino and antineutrino are particles of very, very, very small or almost zero rest mass, okay? But not entirely zero. They still do have some mass, but very, very small. And up till now, research has not been able to tell us what the exact masses of the neutrinos are. But that is research that is still going on. And the spin of the neutrino is 1/2. So they are also emitted in beta decay together with the electron. And so when we introduce the neutrino and the antineutrino, we are able to get rid of the discrepancies which we got in our previous beta decay formula, So this particle Pauli called it the neutrino, little neutral one, because it does not have any charge, okay? They do not have any charge, and it would carry off energy equivalent to the difference between the kinetic energy maximum and the actual kinetic energy of the electron. So as I said before over here, also I mentioned that seldom are the emitted electrons found with an energy of the kinetic energy, maximum kinetic energy that they should have. But they don't actually have the kinetic energy, and the discrepancy between those energies is carried off by the neutrino. Okay? So the neutrino's linear momentum exactly balances those of the electron and the recoiling daughter nucleus. So the neutrino, when we introduce a neutrino, it solves the whole problem. Okay? So then there are two kinds of neutrinos involved in beta decay. The neutrino, which is symbol nu, and the antineutrino, which is symbol nu with a bar on top of that. Okay? So distinguish this. So in order beta decay, it is an antineutrino that is emitted. So remember we mentioned before that beta decay would be neutron going to a proton plus electron. Actually, an antineutrino is also emitted in this reaction. So this is the complete equation for beta decay. Okay? So the neutrino hypothesis has turned out to be completely successful. Okay? So the neutrino mass was not expected to be more than a small fraction of the electron mass because kinetic energy is observed to be equal. To the value carried from this. So the neutrino mass is believed to be the mass equivalent of at most a few electron volts. So the neutrino mass is very small. It's not very large. It's quite small, almost close to zero. But there is still some mass, but very close to zero. And it does not have any charge, and mass is very small, and so it does not have any electromagnetic interactions. So it can pass through neutrinos. Some properties of them is that it can pass through a large amount of matter without any interaction. So that was about neutrinos, and then we will talk about positron and emission and electron capture. So we talked about, remember, we talked in the previous PowerPoint, we also talked about positron emission and electron capture. So maybe I should just make this a bit small here. And so you can see this PowerPoint as well. Well, it's not really clear from here, but what we're saying in the positron emission, pehle humne proton will go to a neutron plus electron. It actually emits a neutrino as well. So positrons were discovered in 1932. 2 years later, were found to be spontaneously emitted by certain nuclei. Positron, we already mentioned what a positron is. It's basically an electron, except it has the same mass as an electron, but an opposite charge. Positron's emission corresponds to conversion of a proton into a neutron and an electron. Proton converts to a neutron and a positron with the emission of a neutrino. So whereas, okay, so
ये न्यूट्रिनोस डिस्कवर कैसे किए थे जब ये रिएक्ट ही नहीं करते?
रिएक्ट नहीं करते, इलेक्ट्रोमैग्नेटिकली रिएक्ट नहीं करते, लेकिन फिर भी डिस्कवर तो हुए ना, because they were discovered to be because of this remedy that we needed.
Okay, ma'am.
To solve the problem of the lack of conservation of the linear momentum, energy, angular momentum, spin, etc. They were proved to be true, to exist because of this discrepancy, that they solve the problem of this discrepancy. Okay? So basically now what we have over here, closely connected with positron emission, we talked about electron capture last time as well. Okay? So last time हमने कहा था कि electron capture में proton plus electron will go to a neutron. Proton plus electron will go to a neutron, but there's also a neutrino emitted in that reaction. And these reactions are improved from the previous theories that were mentioned, because these we have a conservation of all the laws that I mentioned before are conserved when we are talking about when we involve the neutrino and the antineutrino as well. So electron capture is competitive with positron emission, since both processes lead to the same nuclear transformation. As we see over here, positron emission, we have a neutrino released, and we have the final product is a neutron, and in both sides over here, and neutrinos as well. Just the difference between positron emission and electron capture is that electron is captured by the proton, then we get neutron, neutrino. But positron emission, we have a proton that breaks down to a neutron and positron and neutrino. So they're slightly different. But electron capture occurs more often than positron emission, because electrons in such nuclei are relatively close to the nucleus, which promotes interactions with it. So electron capture occurs more often than positron emission in heavy nuclides. Why? Because in heavy nuclides, जिनमें ज़्यादा nucleons होंगे, heavy nuclides, electrons are relatively closer to the nucleus, and because of that, they will interact more with the nucleus. So we get electron capture occurs more often than positron emission. So nearly all the unstable nuclei are found in nature are found with, that's not important. Well, okay, now we will talk about inverse beta decay. And inverse beta decay is, we see that electron capture by a proton is equivalent to proton's emission of a positron. Electron capture by a neutron, similar absorption. So we will talk about inverse beta decay, where an antineutrino is equivalent to the emission of a neutrino and vice versa. So basically we talked about we can take this neutrino, if we put it on the other side of the equation, it becomes an antineutrino. So it becomes proton, here we get proton plus antineutrino will go to, this is inverse beta decay, okay? Will go to neutron plus positron. Neutron plus positron will remain as it is. Just this neutrino in reverse beta decay will just take this neutrino and make it an antineutrino on that side of the equation. Similarly, this neutrino we'll take it on that side of the equation. It'll become an antineutrino, and we will take this electron and it will go on the other side of the equation. So basically, inverse beta decay is like, these are two reactions that define inverse beta decays, but they have very low probabilities to occur. That is why neutrinos and antineutrinos are able to pass through. Inverse beta decay has very low probability to occur. Okay? So these are some of the reactions that involve inverse beta decay. So inverse beta decay involves antineutrinos at the beginning of the reaction. And on the other hand, positron emission, electron capture involve neutrinos that are released, and beta decay involves an antineutrino that's released. So these are some important reactions that you should know. Now we'll talk about gamma decay. Now, what do we know about gamma? We haven't discussed this much more in detail before, but we said that a nucleus which is in its excited state means it's usually denoted by an asterisk. It means that it has higher energy than a nucleus that is in its ground state. It has energies higher than that of its ground state, so it wants to release that energy. It's called an excited nuclei. It wants to return to its ground state by emitting photons, whose energy correspond to the energy difference between the initial and the final states. Like if you take the difference between the final energy and the initial energy of this, for example, an excited nucleus versus the final state of the nucleus, then that is the energy that is released, and that is emitted in the form of gamma rays. That is emitted in the form of photons, which are gamma, which here we will talk about gamma rays. They're emitted in the form of gamma rays. So this is another form, the third form of radioactive decay. The photons emitted by nuclei range in energy up to several mega electron volts. Okay, now we have some mathematics to do. Cross section. So this is going to take some time as well. So are there any questions so far? We still have 10 minutes, so I think we should do this cross section as well. So most of what we know, are there any questions so far? No questions? Okay, then we'll continue here. So what do we know about cross section? We already discussed about that when we were talking about atomic structure, when we were talking about Rutherford scattering. जिसमें हमने कहा था कि क्रॉस सेक्शन में क्या होता है कि अगर हमारे पास एक स्लैब ऑफ मटेरियल है, उसका थिकनेस है dx, thickness is dx, and its area is given by, we have sigma, which is the cross section of that particle for that particular nucleus. What do we mean by cross section? Like अगर हमारे पास एक circle है यहाँ पे, और this is the center, then it will be, suppose if this is our impact parameter, then we said that cross section was equals to pi b squared, right? So here we're talking about cross section in a slightly different context. We are talking about it with respect to decaying of particles. So we had already introduced cross section when we were talking about Rutherford scattering. But here we're going to talk about it in the general sense of when we have some material. So suppose we have a slab of some material whose area is A, whose thickness is dx. N is the number of atoms per unit volume. So N is the number of atoms per unit volume, and sigma is the cross-section area of that, and dx is the width of that. So sigma dx will be the volume, and N is the number of particles per volume. So dN by N will be given by interacting particles divided by incident particles is given by aggregate cross-section divided by target area. And aggregate cross-section is given by NA sigma dx divided by target area, which is A. If you look at this diagram over here, A is this area here. That is our target area. N atoms per unit meter cube will be given by N, which is the number of atoms per meter cube. You have to multiply that by the volume, total volume of the slab, which will be what? A times NA times dx. And then you have to multiply that by sigma as well to get the aggregate cross-section. Each nuclei, a total of NA dx nuclei is in the slab, since the volume of the slab is A dx. Each nucleus has a cross-section of sigma for some particular interaction. So the aggregate cross-section of all the nuclei in the slab is NA sigma dx. Then we have to find, so interacting particles is divided by incident particles. So basically what we're saying here is that if we have incident particles, some of them will interact with this material, some of them will just pass through. So what we want to find out, we want to find an equation for the number of interacting particles divided by incident particles. Okay? Incident particles is the total number of particles that are trying to pass through this material, and interacting is a number that will interact. So in total number of particles is proportional to the area that's passing through this area will be proportional to the area. Okay? And interacting particles will be proportional to NADX, and that will also be, there will also be product with sigma. So basically dN by N will be equal to N sigma dx. Is this making sense?
Yes, ma'am.
If there are N incident particles in a bombarding beam, the number dN that interact with the nuclei in the slab is given by N sigma dx. Where what is sigma over here? Sigma is the cross section for each nucleus of that particular slab. Yeah, ठीक है? With the nuclei in the slab. So sigma is a cross section of each nucleus in the slab. So basically, if we have that slab over here, ठीक है? So we have a cross section of each nucleus in that. Each nucleus in that slab contains a cross section, which is the sigma is equals to pi b squared. And here we're not going to be talking about b, we'll just call it sigma, but we already discussed what sigma is before, so we know what that is. So basically we have this equation for dN by N, the number of fraction of the interacting particles divided by incident particles will be equal to N number of particle and atoms per unit volume of the slab material times sigma dx. Okay? So now what we will do here, now we will yeah, this is the same thing over here. So now we will denote the initial number of incident particles by N naught. So we take this equation now, and to take the integral of this equation, take the integration on both sides of this equation. So is part ko hum N naught, which is the initial number of incident particles, to N, which is the number of surviving particles, which are the ones that pass through the slab. Okay? So N naught is the initial number of particles to N, which is the number of surviving particles. We take the integration, and from 0 to x, we take the integration of 0 to x. Why are we considering x here? Where x is suppose the thickness of the slab from 0 to x. Okay? dx is a small amount of the slab. Small thickness of the slab. We're taking the integral of dx from 0 to x. So when we solve this equation, we will get n is equals to n naught e power minus n sigma x. So the number of surviving particles, n, as we can see from this equation, it decreases exponentially with increasing slab thickness x. Okay? So obviously that makes sense to us because जितनी ज़्यादा इस slab की thickness होगी, उतना ज़्यादा हमारे पास n कम होगा, right? Because its exponential is negative with a negative power. So the more that x is, the smaller this will be, the fraction this will be, right? And so we will have a smaller number of surviving particles. ठीक है? That means that जितनी thickness ज़्यादा होगी, उतनी ज़्यादा the number of fraction of particles that interact will be larger, and the surviving particles will be smaller. Surviving particles will be smaller. So the customary unit for nuclear cross section is the barn. ठीक है? Nuclear cross section जो है उसको barn हम units में लिखते हैं. One barn is equivalent to 10 power minus 28 meters square, and the reason why it's introduced, it's not an SI unit, but it's a handy unit for cross section because cross section is obviously very small. Okay? We're talking about the atomic level here, level of the nucleus, so which are very small. So we need a unit that will be very small. So one barn is 10 power minus 28 meters squared, which is equals to 100 femtometers squared. Okay? So this is the unit for that. Cross sections for most we will do up till here, okay? Because we have some, and maybe we can do an example as well, but that's a bit long. But anyway, we have over here, so the cross section for most nuclear reactions depends on the energy of the incident particle. Okay? So shows this figure over here shows us the cross section as a function of the neutron energy. Okay, so cross section depends on the energy of the incident particles. So the figure shows the neutron capture cross section, where how the neutron capture cross section of 113 cadmium 48 varies with neutron energy. Okay, so we have this particular particle. This nucleus here, it gives off gamma radiation, and it becomes converted to 114 cadmium. It releases a neutron as well, okay? And this reaction neutron is absorbed. Wait, when we mention a reaction like this bracket में जहाँ पे इसका ये bracket में आता है, ठीक है? That means that it's 113 cadmium. It absorbs a neutron. And what's left is 114 cadmium with the release of a gamma ray, emission of a gamma ray. So this is a particular reaction, and when the cross section for the reaction varies strongly with reaction energy. So we get a diagram that looks like this. This is for the cross section of how it varies with neutron energy. Okay, as we can see over here, यहाँ पे maximum we get some peak over here. Okay. Can we do an example, or are we out of time? So a neutron passing through a body of matter, not absorbed. So basically they're saying here that we have a particular a neutron passing through a body of matter and not absorbed in nuclear reaction undergoes frequent elastic collision with some of its kinetic energy is given up. Okay, what they're saying here is that the cross section of 113 cadmium for capturing thermal neutrons is this much barns. The cross section, as we said, that its unit is in barns. The mean atomic mass of natural cadmium is 112 U, and its density is this. What is a fraction of an incident beam of thermal neutrons what fraction of an incident beam of thermal neutrons is absorbed by the cadmium sheet? 0.1 millimeters thick. So we have X is 0.1 millimeters. X is 0.1 millimeters, which is 10 raised to the power minus 4 meters here. 113 cadmium constitutes 12% of natural cadmium. So the number of 113 cadmium atoms per cubic meter is 0.12 times its total mass divided by, now we're using the same procedure as we have done several times before to find the number of atoms per cubic meter. What fraction is so to find the number of atoms per cubic meter, we have to divide the total mass by its density, right? Divide total mass by the number of atoms, that the mass per atom. Okay? So we know that this is the total mass of this cadmium here. Where is this total mass? This is the where'd it go? 8.6 times 10 raised to power 3 kilogram per meter cube is its density. Okay? So as we have done before, number of atoms per cubic meter will be what? Density mass, sorry, this will be mass per cubic meter, mass per cubic meter divided by, and we have to convert this mass into number of particles. So how will we do that? We have to take this density and divide that by 112. 112 is the number, what do you call it? The number of the mean atomic mass.
Volume and density by mass.
Yeah, density, no. Density here and divided, this is the mass, kilogram per unit, per atomic unit, and we have the number of atomic units per atom. So this U will cancel, we will get kilograms per atom, and then kilogram cancel, we will get atoms per meter cube. तो इसलिए इस तरह से हमारे पास ये आ गया है, ठीक है? So this is the number of cadmium atoms per cubic meter, and because cadmium constitutes 12% of natural cadmium, 113 cadmium constitutes 12% of natural cadmium, we have to multiply this by 12%. And obviously I would give that in the question if something like that comes, okay? So then we have the capture cross section is 2.10 raised to the power 4 barns, which we already had. So we write that in meters. So n sigma is what we want to find now. So n is this number, and we have sigma here, so we multiply them. And then we have this formula here, n is equals to n naught e power minus n sigma x, the fraction of incident neutrons that is absorbed. What are they asking us to find? They're asking us to find what fraction of an incident beam is absorbed by the cadmium sheet. So fraction of incident number is n naught. Fraction, this is n is the number of surviving particles. So fraction that is absorbed is n naught minus n divided by n naught. So then for n, we will substitute this formula here. So n naught, n naught, n naught cancels. We will get 1 minus e power minus n sigma x. And x here is 10 raised to the power minus 4 meters. So we plug that in here with the n sigma, which we have found over here. So we will get 0.67. So basically, which is 2/3 of the incident neutrons are absorbed. And then part B, what does part B ask us? Just one last part over here. What thickness of cadmium is needed to absorb 99% of an incident beam of thermal neutrons? So 99% means that are absorbed means that the surviving fraction is 0.01 or 1%, right? If 99% are absorbed, that means the number that has survived is 1% or 0.01 fraction, okay? So n divided by n naught, which is given by this formula over here, n divided by n naught will be equal to e power minus n sigma x. So we have this formula. So now we will take ln on both sides of the equation. We will get ln 0.01 divided by n sigma with a minus sign. And then we get this number over here is equals to 0.41. Where did the minus go? ln में minus होगा, ठीक है? ln में minus होगा. ये equals to है यहाँ पे. This is not minus. This is equal to. This is equal to. This is equal to. ठीक है? यहाँ पे कुछ in the PowerPoint, this is equal to, and this is not minus. This is not minus. This is not minus. These three are equal to signs. So ln 0.01 अगर आप करें तो शायद वो minus sign आएगा, तो इससे फिर वो minus minus cancel हो जाता है, तो you get this number over here. So cadmium is evidently a very efficient absorber of thermal neutrons. ठीक है? So we get 0.41 millimeters. That is what our answer is. What we needed. What thickness of cadmium is needed to absorb 99% of an incident beam of thermal neutrons. ठीक है? And I think the time is over for now, but we will continue from here for the next lecture. Okay? The mean free path of a particle we will discuss, and then we have to do up till here. And then we will start the next chapter when we finish this. Okay, any questions? Let me download the attendance list. Okay, no questions? Okay, so I hope that this week we should be able to be finished with this chapter, okay? It's we did today from slide number, we did quite some slides today, okay? So we will hopefully finish this chapter in this week, and then we will start particle properties of waves, which is our last chapter for this course. Okay? So that's all for today. If there are no questions, then yeah, and the assignment is to derive that formula. I will upload that question sheet on MS Teams for assignment number 4. That will be due by next Monday. Today is Monday, so that will be due by in 1 week's time. Okay? Okay, so that's all from my side. And yeah, any other questions? If there are no questions, then we can end the meeting now. Okay? Okay, Allah Hafiz. Allah Hafiz.
Allah Hafiz.
Allah Hafiz.